coming to my defense today, either in person or remotely, especially at this very difficult time and under this very challenging situation. Today I'm going to talk about an experimental mathematics approach to several combinatorial problems. So here's the content. First, I'll talk about what is experimental mathematics. Then we'll begin with parking functions. We'll look at the golden node of the C-finite ansatz. Then we'll use experimental mathematics to do the analysis of quicksort algorithms. And finally, we will look at Petersburg-Queen's problem. Then I will have a summary. Okay, so what is experimental mathematics? It is an experimental approach to mathematics in which programming and symbolic computation are used to investigate mathematical objects, identify properties and patterns, discover facts and formulas, and even automatically prove theorems. So here's a map of continental USA colored with 4 colors. So we know that in the proof of 4-color theorem, computers were used to check the more than 1,000 reducible configurations. So without computers, the proof might be impossible. And here are some advantages of experimental mathematics approach. It is efficient because we know computers can calculate much faster than humans. It can be easier, it can be automatic, and computers are very powerful. It is less error-prone. Usually humans make more mistakes than computers. It is tireless. Computers do not need to sleep or eat or drink, and they are much more beyond. So I'd like to compare experimental mathematics with machine learning. As we know that machine learning today revolutionized information technology. It can do what humans can. So, for example, humans can distinguish on a photo whether it's a cat or dog. And with machine learning, we just need to analyze the data. We look at a pixel. So for each picture, it will be like 3 matrices. On each matrices, it's just the numbers from, say, 0 to 255. Then from this data, machine learning can distinguish whether it is a picture of a cat or a dog. It can do better than humans. For example, in the game Go, AlphaGo, which are built by deep learning, can beat human world champions. And it can do what humans can't do or what takes too long to do. For example, detect financial fraud for millions of users or even billions of users. The recommended system for each user, online search, and find patterns from big data. So just as machine learning revolutionized information technology, experimental mathematics revolutionized mathematics. It can look for a pattern, test a conjecture, utilize data to make a discovery, prove theorems automatically, provide better tools to maintain and continue building the mathematical skyscraper.
Can I say something?
Yeah. Yeah. Then we begin with parking functions. So here is a map of Hill Center. The blue dot is where we are now. And let's assume in a parallel universe, Friedrich-Hansen Road is a one-way street, say from east to west. And there are several parking spaces, say N, on the southern side of the Hill Center. And at the beginning of the day, all the spaces are available. Then N cars come to park one by one. Each car I has its favorite parking space, number AI. So each car will always go to its favorite parking space first, and then to see what is available. If it is, it will park there. If it's not, it will try to park at the next available parking space. So if all cars can park, we call the preference vector a parking function. So are they parking functions? The first one is a permutation of 9. So it means each car has different favorite parking space. So definitely all cars can park. The same for 1 to 3, 3 to 1. And for 2 to 1, the first car parks at 2, the second car parks at 3, the last car will park at 1. But if it's 2 to 2, then it's not a parking function, because after the first 2 cars parked at 2 and 3, the third car will not be able to park. So here is a formal definition of parting functions. A vector of positive integers from p1 to pn with each pi from 1 to n is a parting function if its non-decreasing sorted version satisfies the ith element is no more than I, because not all cars can park if and only if too many cars prefer a large numbered parking space. So this criteria can guarantee all cars can park. So naturally, we'd like to ask how many parking functions are there for length n. So the number is n plus 1 to n minus 1. And there is a very classical proof. Let's arrange n plus 1 parking space in a circle. Then n cars come to park. Now each car can still choose n plus 1 as their favorite parking space. So totally we have n plus 1 to the n preference vectors. And in this case, we claim that if n plus 1 is the empty space, then it's a parking function. Because definitely all cars can park and there will be one empty space. So let's say if the preference vector is a1, a2 up to an, then the empty space is j. Now let's consider a1 plus I, a2 plus I, up to an plus I. So each number should mod n plus 1. In this case, the empty space will be j plus I mod n plus 1. So it's just a notation. So in this case, we consider I ranges over 0 to n. And in this n plus 1 parking preference vectors, exactly one of them is a parking function. So the answer is n plus 1 to the n divided by n plus 1, which is n plus 1 to n minus 1. And here are some generalizations of parking functions. For example, k hat parking function. So in this one, after we sorting them, the ith element should be no more than ki. And in this case, we can write this k hat parking function as k times an ordinary parking function minus a sequence r1 up to rn, each ri is from 0 to k minus 1. So totally, the number is k to the n times n plus 1 to n minus 1. And more generally, we can have a x vector parking function. So in this case, obviously the number depends on the vector. But our focus is the next one, which is called a parking function. So a vector is an a parking function if its non-decreasing sorted version satisfies that the ith element is no more than a plus I minus 1. So when a is 1, it is just as a usual parking function I mentioned. And we will focus on a parking functions because from a parking functions, we can have our experimental mathematics motivated proof of the number of parking functions. So if we let C of NA be the number of sorted A parking functions of length n, then we have this recurrence relation because we just need to consider the number of ones. If there are k ones, then we delete them. And we consider ak plus 1 minus 1 up to an minus 1. So this is an a plus k minus 1 parking function of length n minus k. So similarly, if Pna is a number of a parking function, we still consider the number of ones. But in this case, if there are k ones, we need to consider the location. So in the recurrence relation, we have the extra term n choose k. So now with experimental mathematics and the maple programming, we have get a result. So from this one, we can conjecture P of NA equals to A times A plus N to the N minus 1. So we want to prove it. We can prove by induction. So first, check the initial condition. Then by induction, we just need to prove this identity. So we define the function f of x. Then basically what we need is a binomial theorem because on this line we use the binomial theorem. Then we plug in x equals to a plus n minus 1. Then we get the number for a parking functions. And when a equals to 1, this is exactly n plus 1 to n minus 1. And now we look at another combinatorial object labeled rooted stories. So we consider labeled rooted stories with a components, where the roots are from 1 to a, and the total number of vertices are a plus n. So we let T of NA denote the number of such stories. Then first we check the initial condition. They are exactly the same with P of NA. Then we consider the number of neighbors of the vertex 1. We remove them with their subtrees and delete the vertex 1. So in this case, there are a plus k minus 1 components and n minus k non-root vertices. So hence we have the same recurrence relation. So from this we can see T of NA equals to P of NA. So since their numbers are the same, naturally there are lots of bijections from them. So we discover or possibly rediscover bijection. This bijection can be best demonstrated by examples. So let's consider a two parking function of length 7, 5, 8, 4, 2, 1, 2, 1. So we use a two-line notation. The first line is the vertices. So actually they are non-root vertices. So it's from 3 to 9 because 1 and 2 are the roots. The second line is our two parking function. So we sort the second line. And now we want to interpret the second two-line notation. Our interpretation is that the parent of vertices 3 and 4 is 1, because you can see here is 3 and 4, and the second line is 1. So 1 is their parent. Similarly, 2 is a parent of 5 and 6. So that's how we have this forest. But we are not done yet. This forest is for the two-line notation after sorting the second line. So if when we sort the second line, we also move the first line's elements accordingly. Then actually we will have this two-line notation. We compare this with the previous one. Then we have a map from 3 to 9 to 3 to 9 itself. So what we need to do is just do this transformation on this forest. Then we will have our labeled rooted forest. So what we want to do is map this forest back to this two parking function. So here we need a convention. When we draw the forest for the same parent, we always place its children in an increasing order from left to right. And we want to index each vertex. So the rule is we start from the first level, which is a root, and then also start from left to right. So we have this indexing just from the top left, 1, 2, 3, 4, 5, 6. Then we want to interpret this forest. Our interpretation is that the first line is still the vertices 3 to 9, and for the second line, it should be the index of its parent. So for example, for 3 here, you can see the parent of 3 is 6. The index of 6 is 5, so it should be 5. So here, this is 5. So similarly for 4, the parent of 4 is 3, but the index is 8. So here, this is 8. And then we want to talk about statistics. We can define some statistics in question on some discrete set. So, and also we want to talk about the limiting distribution. So in this part, our focus is the sum and area statistics of a parking function. So for the statistic sum, it's very easy to understand. We just add up all the elements in the parking function. And another one is called area, which is defined as follows. So the reason we call it area is because it is connected to the Brownian excursion. So I'll show it in a minute. Then we can define PMA of X and the QMA of X. They are just a weighted analogs of P of NA. And then similarly, we can get a recurrence relation for P NA of X and Q NA of X. Then from P NA of X, we can get the formula for the expectation of the sum. Actually, this result was obtained by, I think it's already obtained by someone else. But let's look at the summation here. Since summation is connected to the sequence in OEIS A435, this is expectation of the sum of the heights on labeled rooted trees on N vertices. And this was the first sequence in OEIS. And the limiting distribution of the area is Iry distribution, and it's already proved. And the reason why it's called area, so this one is called area statistic, is because, let me choose a histogram first. Then the scale distribution of the area. Because it's connected with the area under the Brownian excursion. So Brownian excursion is that's a Brownian motion starts from 0, the origin, and then we condition on that it arrives at 1, 0. And also between 0 and 1, it always stays above x-axis. So we condition on this, then we consider the area below this Brownian excursion. The distribution of this is called area Iry distribution. There are many types of Iry distribution. We also have map Iry, and we also have Tracy-Whedon Iry distribution. And surprisingly, Iry distribution occurs in many seemingly unrelated problems, mostly in computer science and graph theory. So we just saw that it occurs in parking function. It also occurs in random planar map. And then we want to consider exact expression for the factorial moment. We want to express the factorial moment in terms of a polynomial ak of NA and another polynomial bk of NA. And then it should be ak of NA plus bk of NA times the expectation. So we get these results, the second factorial moment, the third factorial moment, the fourth one, fifth one, sixth one. And then let's talk about C-finite ansatz. This one shows a methodology of experimental mathematics. So what is a golden knot? Once upon a time, there was a knot that no one could untangle. It was so complicated. Then came Alexander's Greek, and in 1 second cut it with his sword. So it means there are some problems which might be very difficult for human approach, but if we can use experimental mathematics, it can be much easier. So in this part, we will describe 2 case studies. In these 2 case studies, we know that the generating function should be rational, and it is easy to bound the degree of the denominator. So then we can just get many data, and then we can straighten a recurrence relation. And C-finite means if a sequence satisfies a linear recurrence relation with constant coefficients, so Fibonacci sequence is C-finite. And a sequence is C-finite if and only if its ordinary generating function is a rational function. So Fibonacci sequence has a rational function as its generating function. And the definition for Bukhara graph, because first we want to consider the number of spanning trees on a Bukhara graph. So it's just a natural definition. Then in a human approach, we want to consider transform matrix. So So for transfer matrix, it means we need to have ordering for all kinds of the forests. So in this case, we want to have some bijection from set partition to the forest. So we want to define the ordering on a set partition. If we have two set partitions, first we compare the number of paths. So the one with fewer paths will come first. And if they have the same number of paths, then we consider each xi, it means a block containing I. We find the first one which are not the same, then we consider the normal graphical order on xj and yj. J is the first one which are not the same. So this is a partition for 3, 1, 2, 3. And here is the ordering. And here's some additional definitions. So if I and j are in the same block, it is equivalent that the vertices of v and I and v and j are in the same component of the spanning forest F. And we say forest F and the subpartition P are consistent if the number of trees in F is precisely the number of paths in the partition P. And P is a partition induced by F. And now we consider transform matrix. So basically we consider the edges which are in GK of n, which is a k by n growth graph, but not in GK of n minus 1, which is k by n minus 1 growth graph. So in this set En, there are 2k minus 1 members. We want to consider for how many subsets of En can transfer some kind of forest in the graph GK of n minus 1 to another kind of forest in the growth graph GK of n. And then for the transfer matrix, we define the ij entry to be the number of sets which can transfer pj, which is the forest consistent with the j's partition to pi. So we have some examples of the transfer matrices. You can see that when k increases, the dimension of the transfer matrix increases very fast. So with transfer matrices, actually we need to do a lot of human work, but with a famous zero on the next page, we are able to find the initial data easily, and then we can get a recursive relation from the data. So this method will be easier than the transfer matrix method, and from this one, we can get more results actually. So the matrix tree theory, if A is a legitimacy matrix of an arbitrary graph G, then the number of spanning trees is equal to a determinant of any cofactor of the Laplacian matrix L of G. So we just need to take the n comma n cofactor, then the determinant is the number of spanning trees of G. So we have some maple procedure. Guess-rec is used to get a conjecture linear recursive relation from a list of numbers. C2R is also a procedure which accepts a recursive relation and outputs a generating function.
I have a question.
Yeah.
I have a question about guess recurrence.
Yeah.
Why didn't you use GFun?
What's that?
GFun is a standard maple package. GFun by Zimmerman and Salving.
Yes, we know about it, but we prefer to have a more homemade one.
Why? Is my question. Why do you not use GFun?
Oh, because it's much better to do your own. It's more flexible. And equally, the ideas are really trivial. It's a linear algebra. So it's much easier to call. But you're right, we could have used GFun.
GFun, as you know, is based on Pennant approximations.
Yes, thanks for information. Yeah, but
do you use Pate approximations?
no. Basically, I did all the programming myself.
Yeah, essentially we did, but
Yeah, we have our own packages. Yeah. Okay, so I'll continue. So the general idea is to have a low enough list of data for the number of spanning trees in the k by n word graph. So here k is fixed and n can go to infinity. Then we use guesswrap to get a recursion relation from the list of data. We use C2R to find a generating function for the recursion relation. Then with a generating function, it is easy to get a number of spanning trees in gk of n, even for very large n. Say like 5 by 1 billion word graph. So this is much faster than calculating the determinant of the cofactor of the Laplacian matrix for large n. And since the number of states of a word graph is finite for fixed k, the number of spanning trees for different n are C-finite sequence. So its generating function must be a unique rational function, hence our result is rigorous. So here are some generating functions. So you can notice that since the degree of the denominator is 2 to k minus 1, we believe this one is a new result, G7 of n, but surprisingly in this one, the degree of the denominator is 48 instead of 64. And more generally, we can consider an arbitrary graph G, and we consider the number of spanning trees in G times Pn. So Pn is just a path. So we also did this for like a cycle, like 3 cycle or 4 cycle times Pn. And then we can also consider the statistic of the number of vertical edges. So we will have a bivariate generating function. So it's very similar. The general idea is that we need to replace some -1 in the Laplacian matrix by -v. Then we recalculate the diagonal elements. So here's some bivariate generating function. Then we'd like to consider almost diagonal matrices. So here, almost diagonal is somewhat a little bit different from the usual definition. So I'll show you in a minute. So the definition of diagonal matrices are the same, but here, the almost diagonal matrix means if an entry is very far from the main diagonal, it should be 0. And if we have two entries, say AI1J1 and AI2J2, if the difference between I1J1 is the same as the difference between I2J2, then AI1J1 should be equal to AI2J2. So here is our data structure. We have a list of 3 elements. The first one is the dimension. The second one is the non-zero elements in the first row. The third one is the non-zero elements in the first column. So we have our procedure. This one is to calculate the generating function for the determinant. So this is the example. If the first row is 2, 3, and the first column 2, 4, 5. And there's another approach which is called symbolic dynamic programming approach. So in this one, we use cofactor extension. So from cofactor extension, we can get a lot of, let's say, a string S. In the string, there will be, we call the elements the children of the matrix. So first we use expand matrix L to do a one-step cofactor extension along the first row. Then we use another method procedure, children matrix L, to find all children of an almost diagonal matrix. And after all children are found, we have a scheme S. Then by the co-fact extension of any element in a scheme, a system of algebra equation follows. Then we just need to solve the system of equations to get the generating function. So here are our procedures. And here's the example. Okay, then let's use experimental mathematics to do analysis of quicksort algorithms. So sorting algorithms are very important in computer science and technology industry. There are many different sorting algorithms. Quicksort, this is the one we will focus today. And merge sort, basically it means we break down the list to lengths of at most 2. Then when the length of 2 is easy to sort them, then we combine the start list to the main list. During the combination process, we do the sorting. We also have bubble sort, insertion sort, selection sort. Their complexity is big O of n squared, so they are not very efficient when n is very large. And quicksort is the most widely used sorting algorithm. We need to randomly choose an element as a pivot. So in this picture, we choose 3 as a pivot. Then we compare each element with a pivot. If the element is smaller than the pivot, we put it on the left side of the pivot. If it is greater than the pivot, we put it on the right side of the pivot. Then for the 2 stabilities, we do this again. So recursively, we can do the sorting. And so far, very little research has been focusing on the explicit formula of the performance and higher moments of quicksort algorithms. It seems only explicit formulas for expectation and variance are previously known by a very complicated human approach. And higher moments seem to be inaccessible by a human approach. So it is easier to consider the number of comparisons of quicksort because it is independent of the implementation. Basically, quicksort is an idea. It only tells we need to do the partition step, but it doesn't say how we will do that. So if we define Cn be the random variable, the number of comparisons, and the little cn is expectation, we have this recurrence relation for little cn. So we define fk of n to be this summation, and our educated guess that the moment should be a multivariate polynomial involving n, h1 of n up to hm of n, for some n, and n depends on the order of the moment. So here's some formal known results. This variance. This is third moment, and this one is fourth moment. So we'd like to consider the number of swaps instead of comparisons. So number of swaps is much more complicated than the number of comparisons because it's dependent on the specific variant, and it is also more significant because usually a swap takes more time and more computing resources than a comparison. So we have several variants here. So first one is variant nulla. It's just as the one I mentioned. Every time we can create a new list, L1 and L2. L1 contains all elements which are no more than a pivot. L2 contains all elements which are greater than a pivot. So in this case, actually, there's no swap involved. But because we need to use new memory to create a new list, this is not space efficient, and it is also not time efficient. Then we have variant 1. In this one, we choose the first or equivalently the last element in the list of length n as a pivot. Then we compare the other elements with a pivot. So we compare the second element with a pivot first. If it is greater than the pivot, it stays where it is. Otherwise, we insert it before the pivot. So this is somewhat different from a traditional swap, but we define this operation as a swap. So generally, every time we find an element smaller than the pivot, we insert it before the pivot. So we define this probability generating function, and then we have this recursive relation because we know that if the pivot is the k's smallest, then we will have k minus 1 swap. And divided by n because for each k from 1 to n is equal likely. Then from this recursive relation, we can get expectation, variance, third moment, and the fourth moment. So we want to improve it a little bit. The second variant is similar to the first one. One tiny difference that instead of choosing the first or last element as a pivot, the index of a pivot is chosen uniformly at random. So for example, we can choose the ith element, which is the kth smallest as a pivot. Then we compare those non-pivot elements with a pivot. So if I is not equal to 1, then we compare the first element with a pivot. If it is smaller than a pivot, it stays there, otherwise it moves to the end of the list. Then, after we comparing all the left side elements with a pivot, we look at those elements whose index are originally greater than I. If they are greater than the pivot, no swap occurs. Otherwise, we insert them before the pivot. So in this one, we need another function, Q of nkit, is a probability generating function of the number of swaps in the first partition step. So here, the length is n, the pivot is the ith element, and it is the kth smallest. T is a symbol. So the number of swaps actually equals to the number of elements which are before k and greater than k, or after k and smaller than k. So if there are j elements which are before k and smaller than k, then we can get a number of swaps. We can also get a range of j. So this is the formula for Q of nkit. It looks like a very complicated summation. And then we can get the recursive relation for Pn of t. So here we have a double sum because it depends on I and k. Then totally there are n square cases, and each situation is equal likely, so divided by n squared. So then we have expectation. You can notice that expectation is the same. But actually, this variance is smaller than the previous one. Here you can notice for the variance, the leading term is 2n squared. But here is 11 over 6n squared. It means by choosing the pivot uniformly random, I mean not only the value but also the location, we can have a more consistent performance because the variance is smaller. Then third moment and fourth moment. Then we have variant 3. This one is the most used version. It's called in-place quicksort. So it means in this one we don't need to create any new list. We don't need any new memory. We do the swap in the list itself. So basically we need 2 pointers, I and j. So the index starts from 1. So first I should be 0. Every time we found an element, array j, which is no more than a pivot, then we increment I by 1. Then here, this step, we do the swap. And after the loop, we do the swap again. Because the last one is a pivot. Then this step is just the recursion. So in this case, we have the recurrential relation for the probability generating function. When its k is smallest, there will be k swaps. So we get this result, expectation, variance. But there's some waste in variant 3, so we want to improve it. So in variant 4, every time when the element a of j is no more than a pivot, actually we don't need to swap ai and aj if they have the same index. So we want to modify the algorithm such that a swap is performed only when the indexes are different. So here, yn of k will be the number of swaps in the first partition step in the in-place quicksort without swapping the same index. So when k equals to n, actually we don't need any swap. When k less than n, then a swap occurs, of course, only when the element is less than pivot. But we also require, before I, there's already some element which is greater than pivot. Because of this, these two indexes will be different. Otherwise, the 2 pointers will be the same. So when k less than n, the probability that there are s swaps will be this formula. Because we just need to consider what is the location of the first element which is greater than the pivot. Then we can get this one. So now we have a probability joint function for the one step, which is q of nkt. Then we get the recurrential relation for pn of t. So we also have expectation and the variance. So for expectation, you can see this is indeed better than the first one because here we have 1 to n log n. So this one is actually log n. So it's the same here, n log n. But here, the coefficient of n is minus 4 over 3. But this one is minus 5 over 2. So this one has a better performance. Then we have variant 5. This one might not be practical, but we find it is interesting as a combinatorial model because in quicksort, if we can choose an element which is closer to the median as a pivot, then the performance will be better than average. So if there's additional information so that we can choose a pivot not uniformly, but maybe something like Gaussian, so it is to our advantage. So let's assume the list is already a permutation of n, but of course we pretend not knowing that the sorted list is from 1 to n. So now the rule is that we choose the first and the last number in the list. We look at the numbers and choose the one which is closer to the median. If they are equal close to the median, then we choose one at random. So this process makes the distribution of all elements different. It means if it's closer to the median, you will have a higher probability to choose an element as a pivot. And this can improve the performance. So here we get the probability to choose each element as a pivot. Then we have this recurrential relation. And for this one, it seems difficult to get explicit formula. So we have this recurrential relation for the expectation of number of swaps. Here, n is a shift operator. And then we consider dual pivot quicksort. We consider the number of comparisons of dual pivot quicksort. So we also get this recurrential relation. And we have expectation, variance, third moment, and fourth moment. So that's something surprising. For dual pivot quicksort, the expectation up to fourth moment have the same explicit formula with one pivot quicksort. So how about number of swaps? So again, it depends on the implementation. So we do an analog of variant 1. So now let's consider the first and the last elements as a pivot. So we need two pivots in this situation. Let's say that I and j. If I greater than j, then we swap them and we still call the smaller one I. So each time, if there's an element less than I, we move it to the left of I. And if an element greater than j, we move it to the right of j. And we call this kind of operation as a swap. Then we have our recursive relation, and we get expectation. So we can see that in this one, the n log n has coefficient of 4/5, which is better than one pivot quicksort. So how about three pivot quicksort? So now there are more things to be defined. For example, how to sort the pivots. We can use one pivot quicksort to sort the pivots. How to partition the list. Because now it's three pivot, it means there will be four sublists. So luckily we can use binary search. And how to sort a list or sublist containing less than three elements, we can also use one pivot quicksort. So again, we get a recursive relation, and then we have the recursive relation for the expected number of comparisons in the three pivot quicksort. And more generally, for k-pivot quicksort, the conclusion is that if we have a long enough list, say n goes to infinity, then the more pivots, the better. It means, say, if we have 5 pivot quicksort and 6 pivot quicksort, we use them to sort a list of less n. So when n is large enough, finally, the 6 pivot quicksort will outperform the 5 pivot quicksort. But for real-world application, the best strategy would be that we adjust the number of pivots when the length of the sublist varies. And for one pivot quicksort, it might be interesting to see whether there's any sampling method for the pivot which can significantly improve the efficiency. So finally, let's look at Pittsburgh-Queen's problem. So what is Pittsburgh-Queen's problem? It asks for the maximal number m such that it is possible to place m white queens and m black queens on an n by n chessboard so that no queen attacks the queen of the opposite color. So here's some nice pictures from articles by Dr. Sloan. This is one of 3 solutions on 5x5 board, a solution on 8x8 board.
Can I say something?
Yeah, sure.
No? Yes. I didn't make those pictures. Those pictures were made by Michael de Vlieger.
Yes, thank you so much. Yeah, because these pictures are on your article, so I thought you made them. Thank you for the clarification. Then this is more general construction by Juby, but actually in a book in 1987 by Andy, I think he already proposed this construction. And so far, only 50 terms are known. So here's our strategy. We want to consider this Pittsburgh-Queen's problem as a continuous problem by normalizing the chessboard to be a unit square. Then we define the W to be the region where white queens are located. And then the non-attacking region, B of W, can be defined as follows, and B can be the region for the black queens. So we want to find the subset of W such that it maximizes the minimum of the area W and the area of black queens. And here's an observation. The queen is able to move any number of squares vertically, horizontally, and diagonally. So W should be a convex polygon or a disjoint union of convex polygons whose boundary consists of vertical, horizontal, and slope +1, -1 line segments. Because otherwise, we can increase the area of white queens without decreasing the area of black queens. So it means each component is at most an octagon. So this one is Rubin's construction. We want to prove at least this is a local optimum. So we use the data structure for the vertices points. So we can see there are two pentagons, and then it's not difficult to find the region of black queens and the areas of white and black queens. Then we can set in the two areas equal, and using the Lagrange multiplier, we can find all the extreme points. So we find the coordinates of these two pentagons for white queens, and similarly for black queens. So the maximum area of this configuration is 7/48. So now we want to consider the maximum area under more restrictions for white queens. So for example, what if the white queens are in a single rectangle? So this one is easy. We just need to get the coordinates of white queens, find out the area, then the largest area is 1/9. Then again, how about white queens are in a single parallelogram? This one has exactly the same answer with the previous one. And how about single triangle? So this one is also easy. So how about the largest area for a single component? So because we already know it is at most octagon, and to minimize the non-attacking area, it should be placed at some corner. So say a lower left corner. Then in this case, it is at most a hexagon. Because you can notice that if it's an octagon, it will be a waste, because on the lower left corner, it should be like a right angle. So let's find out the maximum when it is a hexagon. So generally it looks like this. So we consider the general shape of a hexagon, find the area of white and black queens. So we find the local maximums using Lagrange multipliers. So this is one of the local maximums, but this is not a hexagon actually. This is an optimal triangle with an area of 1/8. So this one, when A, B, C, D are equal, this is a maximum area for a single hexagon. So in next step, we want to consider that the white queens have two components. In this case, we need a cylindrical algebraic decomposition because we can use them to find out the exact optimal parameters and the maximum areas. So say, what if there are two identical squares for white queens? So now we have two parameters. One is the side length, the other one is the coordinate of this point. So we have two squares. Then based on this configuration, we need to find a domain of the parameters A and S. It's not hard to find the area of white queens. But the formula for black queens is very complicated, especially when A is very small. There may be a lot of components for black queens. But here is why experimental mathematics is important, because from experimentation, we found that for some mid-range S, A around 0.23 will always maximize the area. So with this information, we just need to focus on the shape of black queens when A is not far from its optimum. Then we have the area of black queens. And since in the area of black queens, we have the max function, so we want to separate the domain into 4 regions. In each region, we have a polynomial formula for the area of black queens and the white queens. Then we say them be equal. Now here, we need to use a cylindrical algebraic decomposition. So for each situation, we can find A in some range, then S can be given as a function of A. So from this result, we can find the maximum area of white queens, because in this case, it only depends on A. So then we find the maximum area when there are two identical squares. So similarly, we can find the maximum area for two identical isosceles right triangles with the same orientation. It's smaller than the previous one. Then when they have opposite orientations, actually we don't need CAD. In this one, it's easy. It's 1/8. And when one of them is a square, the other one is an isosceles right triangle with the same side length, we still need to use CAD. So this one is larger than two identical squares. Okay, so finally, I'll have a summary. This is a picture from Pi Day homework of experimental mathematics class in spring 2018. Thanks for your attention.